Hello there, and welcome to a gentle journey through the cosmos. Tonight we're drifting far beyond Earth, into the quiet realm of asteroids, those ancient wanderers that have been silently traveling through space for billions of years. These are not the dramatic, world-ending rocks you see in movies, but rather peaceful celestial neighbors with stories as old as time itself, floating serenely through the darkness like cosmic lullabies waiting to be heard. In the vastness of space, asteroids move with a grace that's almost hypnotic. They tumble slowly, end over end, their surfaces catching starlight as they follow paths carved out eons ago. There's something deeply soothing about these ancient stones, the way they drift through the solar system like leaves on a gentle cosmic breeze. Tonight, we'll explore their quiet mysteries together, letting their timeless stories carry us toward rest. If you find these celestial journeys calming, feel free to subscribe for more peaceful explorations of our universe. And if you have your own favorite space facts that help you unwind, share them in the comments below. Others might find the same comfort in these cosmic tales that you do. But for now, let your breathing slow, your mind soften, and allow yourself to float alongside these gentle giants of space. Let's begin. Most asteroids are incredibly ancient, older than anything you've ever touched. While you lie there now, comfortable and safe, imagine rocks that have been drifting through space since before the first mountains formed on Earth. The asteroids we see today are remnants from the solar system's birth, fragments that never quite came together to form a planet. They're like cosmic time capsules, preserving moments from when our corner of the universe was young and chaotic. These ancient stones formed roughly 4.5 billion years ago in the same swirling disk of dust and gas that gave birth to the sun and planets. Back then, space was filled with countless particles, slowly sticking together through gentle collisions. Some grew large enough to become planets, but others remained small, becoming the asteroids we know today. They've been traveling the same orbital paths ever since, patient witnesses to the entire history of our solar system. What's particularly peaceful about this timeline is how slowly everything happened. These weren't violent explosions or dramatic crashes, but gradual accumulations over millions of years. Dust settled onto dust, pebble joined with pebble, all in the quiet vacuum of space where there's no sound to disturb the process. Even today, asteroids continue this ancient dance, following the same gravitational rhythms that have guided them since the beginning. The asteroid belt between Mars and Jupiter is like a vast, quiet neighborhood in space. Despite what science fiction might suggest, it's actually mostly empty, with asteroids scattered so far apart that spacecraft routinely pass through without seeing a single one up close. If you were floating in the middle of the asteroid belt, you might have to travel thousands of miles before encountering another rock. It's a realm of profound solitude, where silence stretches unbroken across millions of miles. The largest asteroid series is so big it's actually classified as a dwarf planet. It's about as wide as Texas, with a surface covered in mysterious bright spots that reflect sunlight like tiny beacons in the darkness. Ceres rotates slowly, taking just over 9 hours to complete one full turn, creating gentle cycles of day and night across its cratered landscape. Scientists believe it may harbor a subsurface ocean, making it a quiet oasis in the cold depths of space. Most asteroids are much smaller than Ceres, ranging from house-sized rocks to boulders no bigger than a car. They come in different types based on their composition, each telling a different story about the early solar system. Some are made mostly of rock and metal, while others contain more carbon-rich materials. The metal-rich ones gleam softly as they tumble through space, their surfaces polished smooth by billions of years of micrometeorite impacts. There's something deeply calming about how predictable asteroid orbits are. Unlike comets with their dramatic, elongated paths, most asteroids follow nearly circular routes around the sun. They're creatures of habit, returning to the same positions with clockwork precision. Astronomers can calculate exactly where an asteroid will be decades or even centuries into the future, a mathematical poetry written in the language of gravity and motion. Some asteroids have become temporary moons, captured by planets for brief cosmic moments before continuing their journeys. Mars has two small moons, Phobos and Deimos, that are likely captured asteroids. They're irregular in shape, more like potatoes than spheres, and they orbit so close to Mars that they complete several trips around the planet each day. Phobos rises in the west and sets in the east as seen from Mars, racing across the Martian sky faster than the planet rotates below. The surfaces of asteroids are often covered in a fine layer of dust called regolith, created by countless tiny impacts over millions of years. This dust is so fine it would feel like flour between your fingers, and it clings to everything due to the weak gravity and lack of atmosphere. When spacecraft land on asteroids, their engines can create clouds of this ancient dust that hang motionless in the airless environment, eventually settling back down in the weak gravitational field. Many asteroids rotate as they travel, creating gentle cycles of light and shadow across their surfaces. Some spin rapidly, completing a full rotation in just a few hours, while others tumble lazily, taking days to turn once. This rotation creates a subtle rhythm in space, like a slow, silent waltz performed for an audience of stars. The changing shadows play across crater rims and rocky outcrops, creating an ever-shifting landscape that never repeats exactly the same way twice. Binary asteroids add another layer of cosmic choreography to this dance. These are pairs of asteroids that orbit around each other, bound together by their mutual gravitational attraction. They pirouette through space as partners, sometimes touching surfaces in an embrace that lasts for millions of years. The smaller asteroid often orbits the larger one like a tiny moon, creating a miniature solar system within our solar system. Some asteroids follow the same orbital path as planets, clustering at stable points called Lagrange points. These are cosmic parking spots where gravitational forces balance perfectly, allowing asteroids to travel along with a planet without falling into it or drifting away. The Trojan asteroids share Jupiter's orbit, scattered into two groups that lead and follow the giant planet like a cosmic parade. They've been traveling together for billions of years, a perfect example of celestial harmony. Water ice has been discovered on several asteroids, hidden in permanently shadowed craters near their poles. This ice has probably been there for millions of years, protected from the sun's warmth by the asteroid's own shadow. It exists as a kind of cosmic time capsule, preserving water that might be older than life on Earth. Sometimes, when an asteroid's rotation shifts slightly over thousands of years, sunlight reaches these hidden deposits, causing the ice to sublimate directly into space in gentle, invisible streams. The asteroid Vesta is like a museum of early solar system history. Its surface bears the scars of ancient collisions, including a massive crater near its south pole that's so large it can be seen from space. This impact was so powerful it sent chunks of Vesta flying through space, some of which have eventually fallen to Earth as meteorites. By studying these meteorite samples in laboratories, scientists can learn about conditions on Vesta without ever leaving our planet. Near-Earth asteroids occasionally pass close to our world, but most pose no threat. They follow their own orbital schedules, crossing Earth's path at predictable times and distances. Many of these visitors are quite small, no bigger than school buses, and they often go unnoticed as they silently slip past. Their closest approaches happen with the same regularity as celestial clockwork, marked not by drama but by the quiet precision of orbital mechanics. Some asteroids have been found to contain organic compounds, the carbon-based building blocks of life. These materials formed in the cold depths of space, where chemical reactions proceed slowly over millions of years. The discovery suggests that the ingredients for life might be common throughout the universe, drifting quietly through space on countless asteroids, waiting for the right conditions to spark something extraordinary. The asteroid Bennu, recently visited by NASA's OSIRIS-REx spacecraft, rotates so rapidly that loose rocks on its surface occasionally float away into space. This gentle shedding happens without violence or noise, just rocks slowly lifting off and drifting away like seeds from a cosmic dandelion. Some of these particles eventually fall back to the asteroid's surface, while others begin their own independent journeys through the solar system. Asteroid mining might one day provide resources for space exploration, but for now, these rocks remain untouched treasure chests floating in the void. A single metallic asteroid might contain more platinum than has ever been mined on Earth, along with vast quantities of gold, silver, and rare Earth elements. They represent wealth beyond imagination, but they also represent something more profound: the patient accumulation of cosmic materials over billions of years of quiet existence. The study of asteroids has revealed that our solar system is far more dynamic than once thought. Asteroids don't just orbit peacefully, they occasionally change paths due to gravitational interactions with planets. These orbital shifts happen gradually over thousands or millions of years, like a cosmic game of billiards played in extreme slow motion. What seems permanent and fixed from our brief human perspective is actually fluid and ever-changing on cosmic timescales. Tonight, as you rest, these ancient wanderers continue their eternal dance through space, following paths laid down before Earth had oceans or continents. They carry with them the memory of our solar system's birth, silent witnesses to 4 billion years of cosmic history. In their patient orbits and gentle tumbling, there's a kind of cosmic meditation, a reminder that some things move at the pace of eternity itself. Unhurried and serene in the vast darkness between worlds, the gentle pull of gravity shapes every asteroid's journey through space, creating invisible highways that guide these ancient travelers on their endless voyages. Unlike the chaotic collisions you might imagine, most asteroids move through space with remarkable stability, their paths carved by the same gravitational forces that keep planets in orbit. They follow these cosmic currents like rivers of stone, flowing around the sun in patterns so predictable that astronomers can map their movements thousands of years into the future. Some asteroids have surfaces so dark they absorb nearly all the sunlight that touches them, making them almost invisible against the black backdrop of space. These carbon-rich bodies are like cosmic shadows, darker than charcoal, quietly absorbing the sun's energy and radiating it back as gentle warmth. Their surfaces tell stories of chemical processes that unfolded in the early solar system, when organic compounds first began forming in the cold reaches beyond the planets. The rotation of asteroids creates a subtle but constant change in their gravitational fields. As they spin, different parts of their surfaces experience varying amounts of centrifugal force, causing dust and small rocks to migrate slowly across their landscapes over millions of years. This process, imperceptible on human timescales, gradually reshapes these worlds, smoothing rough edges and redistributing material in patterns that follow the mathematics of rotation and gravity. Deep space is filled with asteroid families, groups of rocks that share similar orbits and compositions, because they all originated from the same parent body. Billions of years ago, a large asteroid might have been shattered by a collision, sending dozens or hundreds of fragments into space. These pieces continue to travel together like a scattered constellation, their shared origin revealed by the subtle similarities in their paths through the solar system. The smallest asteroids, no bigger than pebbles, drift silently through space by the millions. They're too small to be tracked individually, but they form a kind of cosmic dust that pervades the entire solar system. When Earth passes through regions dense with these tiny fragments, we see them as gentle meteor showers, streaks of light that paint brief, beautiful patterns across our night sky before burning up harmlessly in the atmosphere. Temperature on asteroids changes slowly and predictably as they orbit the sun. Unlike Earth with its atmosphere to moderate temperature swings, asteroids experience the full range from the sun's warmth to the cold of deep space. But these changes happen gradually over months or years, creating gentle thermal cycles that expand and contract the rock, slowly cracking and reshaping these ancient surfaces, grain by grain. Some asteroids contain pockets of space where tiny particles float freely, held in place by the weak gravitational field but not bound to the surface. These miniature clouds of dust and debris hover just above crater floors, moving in slow motion like underwater snow. They represent some of the most pristine material in the solar system, untouched by planetary processes and preserved in the vacuum of space for billions of years. The concept of seasons exists even on asteroids, though not in the way we experience them on Earth. As they orbit the sun, different parts of an asteroid's surface receive varying amounts of sunlight depending on the tilt of their rotation axis. Some regions might experience years of continuous daylight, followed by years of darkness, creating thermal cycles that span decades rather than months. Binary asteroid systems sometimes experience tidal forces similar to those between Earth and Moon, though on a much smaller scale. These gravitational interactions can cause the asteroids to gradually move closer together or farther apart over millions of years. In some cases, the smaller asteroid spirals slowly inward, eventually making contact with its partner in a gentle collision that takes thousands of years to complete. The discovery of amino acids on asteroids suggests that these wandering rocks might have delivered the building blocks of life to early Earth. These complex organic molecules formed in the cold depths of space, where chemical reactions proceed at their own unhurried pace. They represent a kind of cosmic chemistry set, mixing and combining elements over vast periods of time to create the molecular foundations that might one day spark life. Asteroid surfaces are sculpted by a process called space weathering, where solar wind and cosmic rays gradually alter the composition of exposed rock. This happens so slowly that it's measured in millions of years. But over these vast timescales, it can completely change an asteroid's appearance and properties. The result is a patina of cosmic age, a surface layer that tells the story of billions of years spent traveling through interplanetary space. Some asteroids have been found with magnetic fields, faint echoes of the magnetic environment that existed when the solar system was young. These weak magnetic signatures are preserved like fossilized memories in the asteroid's metallic components, providing clues about the conditions that existed during the earliest phases of planetary formation. They're cosmic time capsules that carry information about magnetic fields that vanished billions of years ago. The gaps in the asteroid belt, known as Kirkwood gaps, are regions where asteroids cannot maintain stable orbits due to gravitational resonances with Jupiter. These empty zones in space represent the subtle but powerful influence of the giant planet's gravity, which over millions of years clears certain orbital paths while leaving others untouched. They're like cosmic highways with missing sections, testament to the invisible forces that shape the architecture of our solar system. Near-Earth asteroids sometimes develop comet-like tails when they pass close to the sun, not because they contain ice, but because solar radiation pressure can blow dust particles off their surfaces. These ephemeral tails are much fainter than those of true comets, visible only to sensitive instruments, but they represent the same process of solar wind interacting with solid matter to create beautiful temporary displays in space. The study of asteroid spectra, the way they reflect different wavelengths of light, reveals their mineral composition without the need for direct sampling. Each type of rock and metal has its own spectral fingerprint, allowing astronomers to identify olivine, pyroxene, iron, and other materials from millions of miles away. This remote sensing creates a kind of cosmic geology, mapping the mineral wealth of asteroids through the patient analysis of starlight reflected from their surfaces. Some asteroids have been found to be rubble piles, loose collections of rocks held together by their own weak gravity, rather than solid, monolithic bodies. These structures formed when larger asteroids were shattered by collisions, with the fragments settling back together into new, loosely bound configurations. They represent a different kind of cosmic architecture, where gravity acts as a gentle glue, holding together collections of ancient debris. The largest asteroids have enough gravity to retain their own thin atmospheres, created by the sublimation of ice or the outgassing of volatile materials from their surfaces. These atmospheres are incredibly tenuous, millions of times thinner than Earth's, but they create a faint envelope around these worlds that can be detected by sensitive instruments. They're like whispers of atmosphere, barely there but still present as evidence of ongoing geological processes. As we drift towards sleep tonight, these countless asteroids continue their patient journeys through space, each one a world unto itself with its own history, composition, and destiny. They move through the cosmos with the unhurried grace of eternity, following paths that were set in motion when the universe itself was young. In their silent orbits and gentle tumbling, there's a profound peace, a reminder that some things in the universe move at the pace of deep time itself, carrying ancient stories through the darkness between stars. Their presence fills the solar system with a quiet grandeur, turning the space between planets into a vast gallery of cosmic sculptures, each one polished by billions of years of patient travel through the infinite night. The Trojan asteroids that share Jupiter's orbit move in a formation that resembles a cosmic convoy, traveling together through space like ancient companions on an endless journey. These asteroid clusters occupy stable gravitational zones 60 degrees ahead of and behind Jupiter, creating two distinct groups that astronomers have named after heroes from the Trojan War. They drift along in perfect synchronization with the giant planet, never falling behind or racing ahead, maintaining their positions through the delicate balance of gravitational forces that has persisted for billions of years. What makes these Trojan asteroids particularly fascinating is how they demonstrate the universe's tendency toward harmony rather than chaos. Instead of colliding or scattering, they've found a way to coexist peacefully in shared space, following Jupiter's lead while maintaining their own individual identities. Each asteroid in these groups has its own unique composition and rotation period, yet they all participate in the same grand orbital dance around the Sun. The asteroid psyche presents one of the most intriguing mysteries in our solar system. This unusual world appears to be made almost entirely of metal, possibly the exposed core of a much larger asteroid that was stripped of its rocky exterior by ancient collisions. Its surface likely gleams with the dull shine of iron and nickel, materials that formed in the heart of the solar nebula when our system was still taking shape. Scientists believe Psyche might offer a unique window into planetary formation, showing us what the cores of rocky planets look like without their outer layers. As Psyche tumbles through space, it reflects sunlight differently depending on which side faces the sun, creating a gentle lighthouse effect that astronomers can observe from Earth. Its rotation period is just over 4 hours, fast enough to create noticeable changes in brightness as different portions of its metallic surface catch and reflect solar radiation. This cosmic beacon has been spinning in the darkness for billions of years, a testament to the conservation of angular momentum that governs rotating bodies throughout the universe. The asteroid Itokawa, visited by Japan's Hayabusa spacecraft, revealed surprising details about how small worlds can maintain their structure in the harsh environment of space. Rather than being a solid rock, Itokawa turned out to be a carefully balanced pile of boulders and debris, held together by gravity so weak that a strong jump could launch you into space. Its surface is covered with smooth areas where fine particles have settled into low-lying regions, creating a landscape that looks almost like a rocky beach frozen in time. What's particularly soothing about Itokawa's structure is how it demonstrates the universe's ability to create stability from apparent chaos. Despite being essentially a loose collection of rocks, this asteroid has maintained its shape and integrity for millions of years. The individual boulders shift and settle occasionally, but so slowly that the process is barely perceptible even over geological timescales. It's like a three-dimensional puzzle that gravity has been patiently assembling for eons. Some asteroids follow highly elliptical orbits that take them from the cold outer reaches of the solar system to the warm inner regions near the sun. These cosmic wanderers experience dramatic temperature changes during their journeys, but these transitions happen so gradually that they unfold over months or years. As they approach the sun, frozen materials on their surfaces begin to sublimate, creating faint halos of gas and dust that dissipate as quickly and quietly as they form. The asteroid belt contains not just rocky debris, but also numerous metallic worlds rich in precious materials. These iron and nickel asteroids formed in the hottest regions of the early solar system, where temperatures were high enough to separate metals from rocky materials. They shine with a subdued luster as they rotate through space, their surfaces polished smooth by billions of years of micrometeorite bombardment that has worn away rough edges and sharp corners. Deep within some larger asteroids, scientists believe there may be networks of caves and tunnels created by ancient volcanic activity or impact fractures. These hidden chambers exist in perpetual darkness, protected from the temperature extremes of space by layers of insulating rock. They represent some of the most stable environments in the solar system, places where conditions might remain unchanged for billions of years. The gravitational influence of asteroids on each other creates a subtle web of interactions that spans the entire belt. While individual asteroids are separated by vast distances, their combined gravitational effects create currents and eddies in the fabric of space-time that influence the motion of smaller debris. These interactions happen so slowly that their effects become apparent only over millions of years, creating a kind of cosmic weather system that operates on geological timescales. Some asteroids contain veins of crystalline materials that formed under extreme pressure during the solar system's violent early period. These crystal formations exist in the asteroid's interior, protected from space weathering and preserved in their original state. They represent natural laboratories where we can study the conditions that existed billions of years ago when the solar system was still settling into its current configuration. The rotation periods of asteroids vary enormously, from rapid spinners that complete a full rotation in just a few hours to slow tumblers that take weeks to turn once. This diversity in rotation rates tells stories about the collisions and gravitational interactions each asteroid has experienced throughout its long history. Fast rotators often show evidence of recent impacts that spun them up, while slow rotators may have been gradually slowed by tidal forces or the radiation pressure of sunlight. Binary asteroid systems sometimes synchronize their rotations through tidal locking, much like how the moon always shows the same face to Earth. In these systems, the two asteroids orbit each other while keeping the same sides permanently facing inward, creating a cosmic dance of mutual gravitational embrace that can persist for millions of years. The locked rotation creates permanent day and night sides on each asteroid, with one hemisphere always bathed in reflected light from its companion, while the other remains in perpetual darkness. Asteroid surfaces accumulate cosmic dust over millions of years, creating layers of fine material that record the history of the solar system's dust environment. This accumulated debris forms a kind of cosmic sediment that preserves information about ancient comet passages, solar wind variations, and interstellar dust that has drifted into our solar system from distant stars. Each layer tells part of a story that spans billions of years of cosmic history. The asteroid Eros, shaped like an elongated potato, demonstrates how gravitational forces can create surprisingly stable systems even with irregular shapes. Despite its odd form, Eros maintains a predictable rotation and orbit, proving that the universe's physical laws work equally well for perfectly spherical worlds and strangely shaped cosmic potatoes. Its surface features include massive boulders that have rolled into crater bottoms over millions of years, coming to rest in the lowest gravitational potential wells. Some asteroids show evidence of ancient water activity with mineral formations that could only have occurred in the presence of liquid water billions of years ago. These hydrated minerals preserve chemical signatures of processes that unfolded when parts of the solar system were warmer and wetter than they are today. They suggest that even in the asteroid belt, conditions once existed that might have supported complex chemical reactions and possibly even primitive forms of life. The study of asteroid families reveals how the solar system has been shaped by countless collisions over billions of years. When a large asteroid is shattered by impact, the resulting fragments continue to orbit the Sun in similar paths, creating identifiable groups that share common origins. These families can be traced back to specific collision events that occurred millions or billions of years ago, providing a fossil record of the solar system's violent past, preserved in orbital mechanics. Near-Earth asteroids occasionally pass so close to our planet that they're visible to amateur astronomers with small telescopes, appearing as slowly moving points of light against the background stars. These close approaches happen with predictable regularity, following orbital schedules that have been calculated centuries into the future. They offer opportunities for detailed study and remind us that we share our cosmic neighborhood with countless ancient travelers who occasionally drop by for brief visits. The surfaces of asteroids preserve impact craters from collisions that occurred billions of years ago, creating landscapes that serve as museums of solar system history. Unlike Earth, where weather and geological activity erase impact scars over time, asteroids maintain their crater records indefinitely in the airless environment of space. Each crater tells the story of a specific collision, preserving details about the size, speed, and composition of the impactor that created it. Some asteroids contain organic compounds that form through chemical processes in the cold depths of space, where reactions proceed slowly over millions of years without the interference of atmospheric or biological processes. These spaceborne organics represent a kind of cosmic chemistry that operates according to different rules than terrestrial processes, creating complex molecules through pathways that remain largely mysterious to scientists studying them from Earth. The gentle process of thermal cycling on asteroids creates patterns of expansion and contraction that slowly reshape these worlds over geological time. As asteroids orbit the Sun, different parts of their surfaces experience warming and cooling cycles that cause rocks to crack and split along natural fracture lines. This process operates so slowly that it's barely perceptible, but over millions of years it can completely transform an asteroid's surface features. Tonight, as you settle into rest, these ancient wanderers continue their eternal journeys through the cosmic dark, each one carrying within its rocky structure the memory of our solar system's birth and the patient accumulation of billions of years of cosmic history. They drift through space with the unhurried grace of deep time itself, following gravitational currents that were established when the universe was young and will continue long after our sun has exhausted its fuel. In their silent orbits and gentle tumbling, there's a profound reminder that some aspects of existence operate on timescales so vast they approach the infinite, moving through space with a patience that transcends all human understanding of time and permanence. The largest asteroids in our solar system contain enough gravitational pull to capture their own small moons, creating miniature planetary systems that operate according to the same physical laws that govern Earth and its lunar companion. These asteroid moons orbit their parent bodies in gentle, predictable cycles, sometimes taking days or weeks to complete a single revolution. The gravitational dance between asteroid and moon creates tidal forces so subtle they can only be measured by the most sensitive instruments. Yet these forces slowly reshape both bodies over millions of years through the patient work of cosmic erosion. What's particularly calming about these asteroid moon systems is how they demonstrate stability emerging from the simplest physical principles. Two rocky bodies, drawn together by gravity's gentle pull, find an orbital balance that can persist for billions of years without external intervention. They neither crash together nor drift apart, instead maintaining a cosmic waltz that continues through the darkness with mathematical precision that would make the most accomplished choreographer envious. The asteroid Didymos and its tiny moon Dimorphos represent one of the most studied binary systems in our solar system. Dimorphos orbits its larger companion once every 11 hours and 55 minutes, a rhythm so regular that astronomers can predict its position years into the future with extraordinary accuracy. This predictability reflects the fundamental orderliness that underlies even the most chaotic-seeming regions of space, where apparent randomness gives way to deeper patterns of gravitational harmony. Some asteroids experience what scientists call mass wasting, where loose material on steep slopes gradually migrates toward lower elevations under the influence of the asteroid's weak gravity. This process happens so slowly that individual particles might take thousands of years to complete their journey from crater rim to crater floor. It's like watching geological processes unfold in extreme slow motion, where landslides take millennia to occur and sediment transport operates on timescales that dwarf human civilization. The color variations visible on asteroid surfaces tell stories of different mineral compositions and exposure ages to space radiation. Some regions appear reddish due to iron-bearing minerals that have been oxidized by solar wind particles over billions of years, while other areas retain the darker hues of unaltered rock. These color patterns create subtle mosaics across asteroid landscapes, painting abstract artworks that have been developing for longer than complex life has existed on Earth. Deep impact craters on asteroids sometimes contain central peaks that formed when the initial collision rebounded, creating temporary mountains that rose from the crater floor before settling into their current configurations. These rebound peaks preserve evidence of the tremendous forces involved in large impacts, where solid rock briefly behaved like a viscous liquid under extreme shock conditions. The peaks now stand as permanent monuments to collisions that occurred billions of years ago when the solar system was still clearing debris from its formation period. Asteroid composition varies dramatically depending on where in the solar system they formed originally. Those that condensed closer to the early sun tend to be rockier and contain more refractory materials that could withstand high temperatures, while asteroids that formed farther out often contain more volatile substances and organic compounds. This compositional gradient reflects the temperature and pressure conditions that existed in different parts of the solar nebula billions of years ago, preserved in the chemical makeup of these wandering time capsules. The phenomenon of asteroid splitting occurs when rotational forces overcome the gravitational binding that holds a loose rubble pile together. As some asteroids spin faster due to thermal radiation pressure or collision effects, centrifugal force gradually overcomes gravity, causing the asteroid to elongate and eventually separate into two or more fragments. This process unfolds over thousands of years, so slowly that it appears static from our perspective. Yet it represents one of the ways new asteroids are born in the modern solar system. Some asteroids show evidence of having been partially melted in their early history, when radioactive elements within their cores generated enough heat to create magma oceans beneath solid crusts. These differentiated asteroids developed layered structures similar to planets, with dense metallic cores surrounded by lighter rocky mantles. The cooling and solidification of these miniature worlds took millions of years, during which they experienced their own geological evolution on a much smaller scale than terrestrial planets. The asteroid Lutetia displays surface features that suggest it underwent a complex geological history involving multiple episodes of heating, cooling, and impact modification. Its landscape includes both ancient, heavily cratered regions and younger areas with fewer impact scars, indicating that different parts of its surface have been exposed to space for varying amounts of time. This heterogeneous surface preserves a record of the asteroid's evolution that spans billions of years of cosmic history. Radar observations of asteroids reveal internal structures that often surprise scientists with their complexity. Some asteroids contain large voids or cavities within their interiors, created either during their formation process or by subsequent impacts that excavated material without completely destroying the parent body. These hidden chambers exist in perpetual darkness and silence, representing some of the most isolated environments in the solar system where conditions might remain unchanged for geological epochs. The process of regolith formation on asteroids occurs through the gradual pulverization of surface rocks by countless micrometeorite impacts over millions of years. Each tiny collision chips away microscopic fragments that eventually accumulate into layers of fine dust covering the asteroid's surface. This cosmic sandblasting operates continuously, but so gently that it takes millions of years to produce noticeable changes in surface texture and composition. Binary contact asteroids represent systems where two separate bodies have touched and merged while maintaining their individual identities, creating dumbbell-shaped objects that rotate as single units while preserving evidence of their dual origin. These contact binaries formed when orbital decay brought two asteroids together at extremely low velocities, allowing them to stick together rather than shattering upon impact. They now tumble through space as unified objects while retaining the distinct characteristics of their component parts. The thermal inertia of asteroid surfaces determines how quickly they respond to temperature changes as they orbit the Sun, creating complex patterns of heating and cooling that vary depending on the physical properties of surface materials. Rocky areas with high thermal inertia warm up and cool down slowly, while dusty regions with low thermal inertia experience rapid temperature fluctuations. These thermal variations create expansion and contraction cycles that gradually fracture rocks and redistribute surface materials over geological time periods. Some asteroids follow orbits that bring them into gravitational resonances with multiple planets simultaneously, creating complex orbital dynamics that can remain stable for millions of years, despite the competing influences of different massive bodies. These multi-body resonances demonstrate the solar system's remarkable ability to find stable configurations even in apparently chaotic gravitational environments, where multiple large planets exert competing influences on smaller objects. The discovery of water vapor emissions from certain asteroids suggests that these bodies contain more volatile materials than previously expected, with subsurface ice deposits that occasionally sublimate when exposed to solar radiation. These water releases happen episodically and unpredictably, creating temporary comet-like activity that quickly fades as the exposed ice is depleted. Such discoveries remind us that the boundary between asteroids and comets is less distinct than once believed. Asteroid surface temperatures can vary by hundreds of degrees between day and night sides, creating thermal environments more extreme than anything experienced on planets with substantial atmospheres. The airless surfaces of asteroids experience the full range from the sun's warming radiation to the cold of deep space, with no atmospheric buffering to moderate these temperature swings. Yet these extreme variations occur gradually as the asteroid rotates, creating predictable thermal cycles that have persisted unchanged for billions of years. The magnetic properties of some asteroids preserve records of ancient magnetic fields that existed in the early solar system, when the solar nebula may have been threaded with magnetic field lines that influenced the formation and migration of rocky materials. These paleomagnetic signatures are locked into metallic grains within asteroid materials, creating a fossil record of magnetic conditions that prevailed during planetary formation processes that concluded billions of years ago. Spectroscopic studies of asteroids reveal absorption features that indicate the presence of hydrated minerals, suggesting that liquid water once interacted with rocky materials in these bodies' early histories. The formation of these hydrated phases required specific temperature and pressure conditions that may have existed when asteroids were larger or when they contained more radioactive heating sources. These mineral signatures preserve evidence of aqueous processes that occurred in environments very different from the cold, dry conditions that characterize asteroids today. The phenomenon of asteroid families extends beyond simple collision fragments to include complex evolutionary relationships, where multiple generations of impacts have created hierarchical structures of related objects. Some families show evidence of cascade collisions, where the breakup of one large asteroid created fragments that subsequently experienced their own catastrophic disruptions, generating multiple generations of debris that share common ancestry but display increasingly diverse characteristics. Asteroid rotation states sometimes exhibit complex behaviors, including tumbling motions, where the rotation axis itself precesses through space, creating intricate patterns of movement that can persist for millions of years. These non-principal axis rotations often result from asymmetric shapes or internal mass distributions that prevent simple spinning motion, instead creating elaborate three-dimensional dances as these objects travel through space following gravitational highways carved by planetary influences. The process of space weathering affects different types of asteroids in distinct ways depending on their composition and structure, creating surface modifications that accumulate over millions of years of exposure to solar wind particles, cosmic rays, and micrometeorite bombardment. These weathering processes gradually alter the optical and physical properties of asteroid surfaces, creating patinas of cosmic age that tell stories about the length of time these objects have spent traveling through interplanetary space. Some asteroids show evidence of having experienced multiple episodes of disruption and gravitational reaccumulation throughout their histories, creating complex internal structures where fragments from different time periods are mixed together in arrangements that preserve geological records spanning billions of years. These multi-generational rubble piles represent natural archives of solar system evolution, where each component carries information about different phases of cosmic development. The orbital evolution of asteroids over geological timescales involves gradual changes driven by subtle forces, including solar radiation pressure, gravitational perturbations from planets, and the Yarkovsky effect, where thermal emission creates tiny but persistent thrust forces that can significantly alter trajectories over millions of years. These evolutionary processes operate so slowly they're barely perceptible over human lifetimes, yet they've been reshaping the asteroid population continuously since the solar system's formation. Tonight, as consciousness fades toward the gentle embrace of sleep, these countless ancient wanderers continue their patient journeys through the cosmic darkness, each one a world unto itself, carrying stories written in stone and metal across billions of years of silent travel. They move through space with the unhurried dignity of deep time, following paths that were established when the universe was young and will continue long after the last stars have dimmed. In their eternal orbits and gentle tumbling motions, they embody a kind of cosmic serenity that transcends all human measures of time and change. Drifting peacefully through the infinite night like dreams made of stone and starlight, forever traveling the ancient highways carved by gravity's patient hand through the vast cathedral of space. The gravitational resonances that govern asteroid motion create invisible musical harmonies throughout the solar system, where orbital periods align in simple mathematical ratios that produce stability from apparent chaos. Some asteroids complete exactly 2 orbits for every 3 Jupiter makes, while others maintain 3-to-1 or 5-to-2 relationships with various planets. These resonant frequencies operate like cosmic tuning forks, creating zones of stability where asteroids can orbit safely for billions of years without being ejected from the solar system or pulled into planetary collisions. What makes these resonances particularly soothing is their predictability and permanence. Once an asteroid settles into a resonant relationship with a planet, it can maintain that mathematical harmony for the entire lifetime of the solar system. The gravitational forces involved are so precisely balanced that these objects essentially sing together in frequencies measured not in sound waves, but in orbital periods, creating symphonies of motion that play out across millions of years. The asteroid Apophis, famous for its close approaches to Earth, demonstrates how precisely astronomers can calculate orbital mechanics. Despite initial concerns about potential impact risks, careful observation and mathematical modeling have shown that Apophis will pass safely by our planet for centuries to come. Its orbit has been traced with such accuracy that scientists know exactly when and where it will appear in Earth's sky, decades into the future, a testament to the clockwork precision that governs celestial mechanics. During its closest approach in 2029, Apophis will pass near enough to Earth that it will be visible to the naked eye as a moving point of light against the background stars. This close encounter will cause our planet's gravity to slightly alter the asteroid's orbit, demonstrating how gravitational interactions can modify celestial paths over time. Yet even this perturbation is entirely predictable, with astronomers able to calculate exactly how Apophis's future orbit will change due to Earth's gravitational influence. Some asteroids contain materials that formed under conditions no longer present anywhere in the solar system, preserving samples of environments that existed only during the earliest phases of planetary formation. These primitive bodies contain pre-solar grains, microscopic particles that formed around other stars before our solar system even existed. These ancient relics traveled through interstellar space for millions of years before being incorporated into the forming solar nebula, making them among the oldest materials accessible to scientific study. The preservation of these pre-solar grains within asteroid matrices represents a kind of cosmic archaeology, where we can study the products of stellar processes that occurred billions of years ago in distant parts of our galaxy. Each grain carries isotopic signatures that reveal details about the nuclear reactions that created them, providing direct samples of stars that lived and died long before our sun was born. Asteroid surfaces sometimes display strange geometric patterns created by thermal stress fractures that form as these bodies experience repeated heating and cooling cycles during their orbits. These fracture networks can create polygonal patterns reminiscent of mud cracks or basalt columns, but operating on much larger scales and over much longer time periods. The cracks propagate slowly through solid rock over thousands of years, creating natural tessellations that divide asteroid surfaces into geometric segments. The formation of these thermal fracture patterns requires specific conditions of rock strength, thermal expansion rates, and cooling timescales that vary from asteroid to asteroid. Some bodies develop fine networks of small cracks, while others form fewer but larger fractures that can extend for kilometers across their surfaces. These patterns remain stable for millions of years once formed, creating permanent geometric artwork etched into these ancient worlds by the patient action of thermal cycling. The asteroid Ryugu, visited by Japan's Hayabusa 2 mission, revealed surprising details about how small worlds can maintain complex surface features despite their weak gravitational fields. Its diamond-shaped profile and equatorial ridge suggest a history of rapid rotation that has redistributed mass toward the equator, creating a spinning top configuration that persists even as the asteroid's rotation has slowed over time. The surface shows evidence of both ancient impacts and more recent processes that continue to modify its appearance. What's particularly fascinating about Ryugu is how its loose, rubble pile structure allows for gradual shape changes over geological time. The weak gravity means that material can migrate across the surface in response to tiny perturbations, slowly altering the asteroid's profile through processes that would be impossible on more massive worlds. This ongoing evolution happens so gradually that it's barely perceptible, yet over millions of years, it can completely transform an asteroid's appearance. Deep within the largest asteroids, conditions may exist that are remarkably stable compared to the temperature extremes experienced on their surfaces. The thermal mass of several kilometers of rock provides excellent insulation, creating interior environments where temperatures remain nearly constant year-round. These protected zones represent some of the most thermally stable environments in the solar system, where conditions might remain unchanged for billions of years. The interiors of large asteroids also experience much lower levels of cosmic radiation than their surfaces, as the overlying rock provides natural shielding from energetic particles streaming through space. This protection creates environments that preserve original materials in pristine condition, unaltered by the space weathering processes that gradually modify exposed surfaces. Scientists believe these interior regions might contain the most primitive samples of early solar system materials. Some asteroids follow highly inclined orbits that carry them far above and below the plane of the solar system, providing unique vantage points for observing the cosmic environment from perspectives unavailable to Earth-based observers. These high-inclination asteroids experience different radiation environments and gravitational influences compared to their more conventionally orbiting cousins, potentially preserving different records of solar system evolution. The extreme orbital inclinations of these asteroids may result from close encounters with planets that scattered them into unusual trajectories billions of years ago. Once established, these tilted orbits remain stable for extremely long periods, carrying their asteroid passengers on journeys that take them through regions of space rarely visited by other solar system objects. They travel like cosmic explorers, sampling conditions throughout the three-dimensional volume of interplanetary space. Asteroid density measurements reveal that many of these bodies are significantly less dense than solid rock, confirming that they contain substantial void spaces within their structures. Some asteroids have densities so low that they would float if placed in water, despite being made primarily of rocky and metallic materials. This low density indicates that they're essentially porous, with internal architectures more like loose gravel piles than solid monolithic rocks. The high porosity of many asteroids affects how they respond to impacts, with the void spaces acting as shock absorbers that can dissipate collision energy more effectively than solid materials. This property may help explain why some asteroids have survived intact through billions of years of bombardment by smaller objects, as their internal structure allows them to absorb impacts that might shatter more solid bodies. The study of asteroid albedos, or reflectivity values, reveals the diverse range of surface compositions present throughout the asteroid belt. Some asteroids reflect less than 3% of incident sunlight, making them darker than charcoal, while others reflect more than 50%, appearing relatively bright against the black backdrop of space. These albedo variations correspond to different mineral compositions and surface textures that tell stories about formation conditions and evolutionary histories. Dark asteroids often contain carbon-rich materials and organic compounds that formed in the cooler, outer regions of the early solar system, while brighter asteroids typically consist of rocky and metallic materials that condensed closer to the young sun. This compositional gradient preserved in the asteroid population provides a fossil record of the temperature and chemical conditions that existed throughout the solar nebula during planetary formation. The rotation periods of asteroids span an enormous range, from objects that spin so rapidly they complete a rotation in just over 2 hours, to others that tumble so slowly they take several weeks to turn once. This diversity in rotation rates reflects the complex collision history each asteroid has experienced, with faster rotators often showing evidence of relatively recent impacts that spun them up, while slower rotators may have been gradually decelerated by tidal forces or radiation pressure effects. The fastest rotating asteroids approach the theoretical limit where centrifugal force would overcome their weak self-gravity and cause them to fly apart. These rapid spinners maintain their integrity through a delicate balance of forces, with gravity barely strong enough to prevent surface materials from escaping into space. Any further increase in rotation rate would cause these objects to shed mass or potentially split into multiple fragments. Some asteroids display seasonal variations in brightness as their rotation brings different surface features into view from Earth's perspective. These brightness changes can reveal information about surface composition variations, the presence of large boulders or crater walls that cast shadows, and even the overall shape of the asteroid. Long-term monitoring of these brightness variations allows astronomers to create detailed models of asteroid surfaces without ever visiting them directly. The seasonal brightness cycles of asteroids provide a kind of remote sensing that reveals surface features through patient observation from Earth. As these objects rotate and orbit, different aspects of their geology become visible, creating natural surveys that unfold over months or years. This technique has revealed everything from massive impact craters to concentrations of reflective minerals that create bright spots visible across millions of miles of space. Binary asteroid systems sometimes exhibit complex orbital evolution, where the two components gradually spiral toward each other due to tidal energy dissipation, eventually leading to gentle collisions that merge the bodies into single contact binary objects. This process unfolds over millions of years as orbital energy is slowly converted to heat through tidal flexing, causing the orbital separation to decrease at rates barely perceptible over human timescales. The eventual merger of binary asteroids creates elongated, dumbbell-shaped objects that preserve evidence of their dual origin in their unusual forms. These contact binaries rotate as single objects while maintaining distinct lobes that reflect their history as separate bodies. The merger process itself is remarkably gentle, with collision velocities so low that both components remain largely intact despite coming together after millions of years of gradual orbital decay. The phenomenon of asteroid splitting demonstrates how rotational forces can overcome gravitational binding in these weakly bound rubble pile structures. As some asteroids spin faster due to thermal effects or collision outcomes, centrifugal force gradually begins to dominate over the weak gravity holding the loose aggregate together. The splitting process occurs slowly over thousands of years, with the asteroid gradually elongating before finally separating into two or more fragments. These newly formed asteroid pairs often continue to orbit each other as binary systems, maintaining their gravitational connection even after the original body has split apart. The separation process creates asteroid families on the smallest scale, where fragments share common origins and similar orbital characteristics, despite now existing as independent objects. Some of these pairs eventually separate completely and follow independent paths through the solar system. Asteroid surface materials undergo continuous modification through a process called impact gardening, where countless small collisions gradually mix and redistribute surface layers over millions of years. Each micrometeorite impact excavates tiny amounts of material, creating small craters, while simultaneously burying other regions under thin layers of ejected debris. This ongoing process slowly homogenizes the upper layers of asteroid regolith while preserving deeper materials in relatively pristine condition. The gardening process operates so slowly that it takes millions of years to mix surface layers to depths of just a few meters. Yet over geological time, it can completely rework the upper portions of asteroid surfaces. This gradual mixing creates complex stratigraphies where materials from different time periods become interlayered, preserving records of impact history in the vertical structure of regolith deposits. Some asteroids show evidence of having experienced catastrophic disruption events that completely shattered the original body, followed by gravitational reaccumulation of the fragments into new, loosely bound structures. These reaccumulated bodies often retained evidence of their violent histories in the form of internal fracture patterns, unusual shapes, and heterogeneous compositions that reflect the mixing of materials from different parts of the original parent body. The reaccumulation process following catastrophic disruption can create asteroid structures that are fundamentally different from objects that form through gradual accretion processes. These disrupted and reformed bodies often have complex internal architectures with large void spaces, unusual mass distributions, and surfaces that display materials originally buried deep within the parent body. They represent a kind of asteroid archaeology where violent events have excavated and rearranged ancient materials. The thermal evolution of asteroids during the early solar system created differentiated structures in the largest bodies, where dense material sank toward the center while lighter components rose toward the surface. This process, similar to what occurred in the terrestrial planets but on a much smaller scale, created layered structures with metallic cores surrounded by rocky mantles and basaltic crusts. Subsequent collisions have exposed cross-sections through these differentiated structures, providing samples of asteroid interiors. Some metallic asteroids may represent the exposed cores of larger differentiated bodies that were stripped of their rocky exteriors by catastrophic collisions billions of years ago. These objects provide unique opportunities to study materials that formed under the high-pressure, high-temperature conditions that existed deep within planetesimals during the early phases of solar system evolution. They are essentially natural laboratories for studying planetary core formation processes. The orbital distribution of asteroids throughout the solar system reflects billions of years of gravitational evolution, where planetary perturbations have gradually sculpted the population into its current configuration. The main asteroid belt represents a dynamically stable region where objects can survive for the age of the solar system, while other populations have been scattered into various reservoirs by planetary migrations and gravitational resonances. Near-Earth asteroids represent objects that have been gradually transported inward from the main belt through complex dynamical pathways that operate over millions of years. These migration routes involve gravitational resonances, planetary close encounters, and subtle radiation pressure effects that combine to deliver main belt objects into Earth-crossing orbits. The process continues today, with new near-Earth asteroids being supplied from the main belt at predictable rates. The study of asteroid crater populations reveals information about the bombardment history of the solar system, showing how impact rates have changed over billions of years as the population of potential projectiles has gradually been depleted. Large asteroids preserve crater records spanning billions of years, with different crater-size distributions, reflecting different epochs in solar system evolution when projectile populations had different characteristics. Ancient crater populations on asteroids show evidence of a period of intense bombardment that occurred during the solar system's first billion years, when planetary migration events stirred up debris populations and created enhanced collision rates throughout the inner solar system. This early bombardment period, preserved in the crater records of asteroids, provides crucial information about the timing and intensity of processes that shape the final architecture of planetary orbits. The composition of asteroid regoliths often differs significantly from that of the underlying bedrock due to contamination from foreign materials, delivered by impacting projectiles over billions of years. This contamination creates surface layers that represent mixtures of indigenous materials and debris from other asteroids, comets, and even interplanetary dust particles that have accumulated over geological time. The contaminated regoliths preserve records of the materials that have bombarded each asteroid throughout its history. Spectroscopic studies of asteroid surfaces can sometimes detect these contamination signatures, revealing evidence of materials that originated in different parts of the solar system before being delivered through impact processes. The contamination layers create natural archives of solar system-wide processes, preserving samples of materials from distant sources that would otherwise be inaccessible for solar system. When the solar nebula was still present, formed in the presence of magnetic fields much stronger than anything information about ancient magnetic fields that may have existed in the early related to magnetic field generation in the early sun study. The magnetic properties of asteroids provide and planetary formation processes were actively occurring. Some asteroids retain weak magnetic signatures that suggest they currently present in interplanetary space, possibly or magnetization processes within the solar nebula itself. These pale left permanent imprints in the magnetic minerals contained within asteroid materials. Magnetic records preserved in asteroid materials offer unique insights into conditions that existed during the earliest phases of solar system evolution, when physical processes very different from those operating today were shaping the formation of planets and smaller bodies. The magnetic signatures represent fossil evidence of electromagnetic environments that vanished billions of years ago, but as the night deepens and consciousness begins its gentle journey toward rest meditation, moving through the universe with unhurried grace that transcends all human measures of time and change, forever following the ancient Rith billions of years, they drift through space with the quiet dignity of deep time, carrying within their rocky structures the accumulated wisdom of eons spent traveling testament to the patient processes that have shaped our solar system over. These countless ancient wanderers continue their eternal dance through the cosmic darkness, each one orbits in gentle tumbling motions. They embody a kind of the gravitational highways that connect distant worlds. In their silent established when the cosmos was young and will endure long after the last stars fade in, to the infinite night. The surfaces of asteroids bear witness to cosmic ray bombardment that has continued uninterrupted for billions of years, with high-energy particles from distant stars and galaxies gradually altering the crystal structure of surface minerals grain by grain. This space weathering creates chemical changes so subtle they can only be detected through sophisticated spectroscopic analysis. Yet over geological time, these modifications accumulate into significant alterations of surface composition and appearance. The process operates like an incredibly slow-motion chemical reaction, where individual atomic interactions add up over eons to transform entire asteroid surfaces. What makes this cosmic ray weathering particularly fascinating is its universality and persistence. Every asteroid surface exposed to space experiences this gradual modification, creating a kind of patina of cosmic age that develops at rates measured in changes per million years. The weathering affects different minerals in distinct ways, with iron-bearing compounds showing the most dramatic alterations as they develop thin rims of metallic iron that change their reflective properties and magnetic characteristics. Some asteroids contain impact melt rocks formed during ancient collisions when kinetic energy was converted to heat, intense enough to temporarily liquefy solid stone and metal. These melt rocks preserve snapshots of extreme conditions that existed for only brief moments during catastrophic impacts billions of years ago, when temperatures reached thousands of degrees and pressures exceeded anything found in terrestrial environments. The rapid cooling that followed these impact events froze these extreme conditions into permanent geological records. The textures preserved in asteroid impact melts reveal details about collision dynamics that would otherwise remain hidden, showing how shock waves propagated through solid rock and how different materials behaved under extreme stress conditions. Some melt rocks contain fragments of unmelted material that were incorporated during the cooling process, creating complex textures that tell stories of chaos and violence preserved in stone for billions of years. Asteroid families that form through catastrophic disruption events often show evidence of subsequent collisional evolution, where family members have experienced additional impacts that modified their shapes, spins, and surface properties over millions of years following the initial breakup event. This ongoing evolution means that asteroid families are not static populations, but continue to change as their members interact with each other and with background populations of smaller projectiles. The study of asteroid family evolution reveals how collision processes operate on different timescales, from the instantaneous disruption that creates the initial fragments to the gradual modifications that accumulate over millions of years of subsequent bombardment. Some family members show evidence of having been fractured and reaccumulated multiple times, creating complex internal structures that preserve records of multiple generations of collision events. The albedo patterns visible on some asteroids suggest the presence of impact rays, bright streaks of material excavated from beneath darker, weathered surfaces by relatively recent impacts. These ray systems, similar to those seen on the Moon but much fainter, gradually fade over millions of years as space weathering darkens the exposed bright material. The presence of visible rays indicates that the impacts responsible for creating them occurred within the last few million years, making them among the youngest features visible on asteroid surfaces. The gradual fading of impact rays demonstrates how space weathering operates as a kind of cosmic clock, with the degree of darkening providing rough estimates of how long material has been exposed to the space environment. Fresh impact craters show bright rays that gradually disappear as the excavated material ages, creating time sequences that can be read in the brightness patterns visible on asteroid surfaces. Some asteroids show evidence of having experienced multiple episodes of heating throughout their histories, possibly due to close approaches to the Sun during periods when their orbits were more eccentric than they are today. These heating events left signatures in the form of thermally altered minerals and modified crystal structures that preserve records of high-temperature conditions experienced long after the asteroid's initial formation and early thermal evolution. The thermal histories preserved in asteroid materials provide insights into orbital evolution processes that operated over billions of years, showing how gravitational perturbations and other dynamical effects have altered asteroid trajectories throughout solar system history. Some asteroids may have experienced orbital changes dramatic enough to carry them from the cold outer regions of the asteroid belt to the warmer inner solar system, where solar heating caused significant thermal modifications to their surface materials. Binary asteroid systems sometimes develop synchronized rotation periods, where both components complete their rotations in the same time it takes them to orbit around their common center of mass. This synchronization occurs through tidal interactions that gradually slow or speed up the rotation rates until they match the orbital period, creating systems where the same faces of both asteroids always point toward each other during their mutual orbit. The process of tidal synchronization in binary asteroids operates over thousands or millions of years, gradually dissipating rotational energy through internal friction as the gravitational forces of each component raise tides in the other. The end result is a configuration that minimizes energy and maximizes stability, allowing these paired systems to persist for billions of years once synchronization is achieved. The asteroid series shows evidence of cryovolcanic activity, where subsurface brines have occasionally erupted through the surface to create bright deposits of salt minerals that stand out dramatically against the darker surrounding terrain. These eruptions represent a form of geological activity that operates under conditions very different from terrestrial volcanism, with liquid brines replacing molten rock and extremely low atmospheric pressures, allowing rapid sublimation of water components. The bright spots on Ceres appear to be relatively young features that continue to evolve as subsurface brines reach the surface and deposit their dissolved minerals through evaporation and sublimation processes. This ongoing activity makes Ceres one of the most geologically active bodies in the asteroid belt, demonstrating that even small worlds can maintain internal processes capable of modifying their surfaces over geological time. Some asteroids contain shock metamorphosed minerals that form during high-velocity impacts, when normal crystal structures were transformed into high-pressure phases that can only exist under extreme conditions. These shock minerals preserve evidence of impact events that generated pressures equivalent to those found deep within planetary interiors, creating exotic phases of common materials that would be impossible to produce under normal surface conditions. The study of shock metamorphosed minerals and asteroids provides insights into impact processes that operated throughout solar system history, showing how collision energies have varied over time as orbital velocities and impact frequencies changed in response to planetary migration and dynamical evolution. These minerals serve as natural laboratories for studying material behavior under extreme conditions that cannot be replicated in terrestrial experiments. The organic compounds found in some asteroids show evidence of having undergone thermal processing that altered their molecular structures without completely destroying their carbon-based chemistry. This thermal processing may have occurred during impact heating events or periods of internal warming due to radioactive decay, creating modified organic materials that preserve information about both their original compositions and the thermal conditions they experienced. The survival of organic compounds in asteroids despite billions of years of space exposure and occasional thermal processing demonstrates the remarkable stability of carbon-based chemistry under the right conditions. These preserved organics provide samples of the chemical processes that were operating in the early solar system, offering insights into the molecular foundations that may have contributed to the origin of life on Earth and possibly elsewhere. Asteroid surfaces often display evidence of mass movement processes where loose material has migrated across the surface under the influence of weak gravity fields and external perturbations, such as impacts or thermal cycling. These mass movement features include landslides that occurred in slow motion over thousands of years, gradual slope failures that redistributed surface materials, and impact-triggered avalanches that carved channels and deposited debris fans across crater floors and valley systems. The extremely slow pace of mass movement on asteroids means that these geological processes unfold over timescales that dwarf terrestrial equivalents, with landslides that might take minutes on Earth requiring millennia to complete on low-gravity asteroids. Yet, the end results create landscape features that would be recognizable to terrestrial geologists, demonstrating how universal physical processes operate under different gravitational conditions to create similar outcomes through different mechanisms. The rotation of some asteroids creates centrifugal forces strong enough to influence the distribution of surface materials, causing fine particles to migrate toward equatorial regions, where the effective gravity is reduced by rotational acceleration. This process can create distinct latitudinal zones with different surface properties, including equatorial ridges, where accumulated material forms topographic highs that circle the asteroid like cosmic mountain ranges. The formation of equatorial features through rotational processes demonstrates how the simple act of spinning can reshape entire worlds over geological time, creating topographic patterns that reflect the balance between gravitational attraction and centrifugal acceleration. These features preserve records of rotation rates that may have changed throughout an asteroid's history due to collision events or other external influences. Deep within the largest asteroids, primitive materials may be preserved in conditions that have remained largely unchanged since the solar system's formation, protected from space weathering, thermal cycling, and impact processing by kilometers of overlying rock. These interior regions represent natural, deep freeze environments where the most ancient solar system materials might exist in nearly pristine condition, offering potential access to samples that predate the formation of planets. The interiors of large asteroids also provide natural laboratories for studying how materials behave under constant low-temperature, low-pressure conditions over billions of years, where chemical and physical processes proceed at rates so slow they approach absolute stability. These environments may preserve isotopic signatures, mineral assemblages, and organic compounds that have been completely altered or destroyed in more dynamic environments elsewhere in the solar system. Some asteroids show evidence of having accreted materials from different regions of the early solar system, creating heterogeneous compositions that reflect the mixing processes that occurred during the final stages of planetary formation. These composite asteroids contain materials with different formation temperatures, chemical compositions, and isotopic signatures that were brought together through collisional and dynamical processes operating over millions of years. The heterogeneous compositions of some asteroids provide natural samples of the diversity that existed in the early solar system, preserving materials from different chemical and thermal environments that would otherwise be difficult to study. These mixed compositions tell stories of the complex processes that operated during the transition from solar nebula to planetary system, when materials from different regions were redistributed through gravitational interactions and impact processes. The discovery of amino acids and other prebiotic compounds in asteroid samples suggests that these bodies may have served as delivery vehicles for the chemical building blocks of life, transporting complex organic molecules from the outer solar system to the inner regions where terrestrial planets were forming. The preservation of these compounds over billions of years demonstrates the protective nature of asteroid interiors, where organic materials can survive exposure to cosmic radiation and thermal processing. The organic chemistry preserved in asteroids represents a kind of molecular paleontology, where we can study the chemical processes that were operating in different regions of the early solar system before life appeared on Earth. These compounds may have formed through reactions between simple gases and minerals in the presence of liquid water, creating molecular libraries that preserve information about the chemical environments that existed during the solar system's youth. Tonight, as you surrender to the gentle embrace of approaching sleep, these ancient wanderers continue their patient journeys through the star-filled darkness, each one carrying within its rocky structure the accumulated memories of billions of years spent traveling the cosmic highways that connect the worlds of our solar system. They move with the unhurried grace of eternity itself, following gravitational currents that were established when the universe was young and will persist long after the last planetary orbits have decayed. In their silent passage through the infinite night, they embody a kind of cosmic meditation, a reminder that some aspects of existence operate on timescales so vast they approach the eternal, drifting peacefully through space like ancient stones carrying whisper-ed stories from the dawn of time. Their gentle tumbling motions and predictable orbits speak of universal laws that govern matter and energy across all scales, from the smallest particles to the largest galactic structures, creating patterns of motion and rest that have persisted since the first moments of cosmic history, and will continue until the stars themselves grow cold and fade into the endless dark between the galaxies. The gravitational resonances that shape asteroid motion create invisible symphonies throughout the solar system, mathematical harmonies where orbital periods align in precise ratios that maintain stability across billions of years. These resonant relationships operate like cosmic tuning forks, creating zones where asteroids can orbit safely without being ejected into interstellar space or pulled into catastrophic planetary collisions. The most famous of these resonances occur with Jupiter, where asteroids maintain orbital periods that are exact fractions of the giant planet's year, creating gaps and concentrations that demonstrate the subtle but persistent influence of gravitational forces operating across vast distances. What makes these resonant patterns particularly soothing is their mathematical elegance and permanence. Once an asteroid settles into a resonant relationship with a planet, it can maintain that precise orbital harmony for the entire lifetime of the solar system. The forces involved are so delicately balanced that these objects essentially dance together in frequencies measured not in sound waves, but in orbital periods, creating celestial choreography that unfolds over millions of years with clockwork precision. The asteroid Vesta reveals layers of geological history written in its heavily cratered surface, where each impact scar preserves a moment from the solar system's violent past. This massive world, nearly as large as some small planets, bears the record of billions of years of bombardment in its scarred terrain. Its most dramatic feature is an enormous crater near the South Pole, so large that it removed a significant portion of the asteroid's mass and sent fragments flying through space that eventually found their way to Earth as meteorites. These Vesta meteorites provide a unique opportunity to study an asteroid's composition without leaving our planet, offering direct samples of materials that formed in the asteroid belt billions of years ago. The meteorites reveal that Vesta experienced extensive melting and differentiation early in its history, developing a layered structure with a dense metallic core surrounded by lighter rocky materials. This geological evolution mirrors that of terrestrial planets, but on a much smaller scale, creating a kind of miniature world that preserves records of processes that shaped all rocky bodies in the inner solar system. Some asteroids follow highly eccentric orbits that carry them from the frigid outer reaches of the solar system to the warm inner regions near the Sun, creating extreme variations in their thermal environments over the course of each orbital cycle. These elongated trajectories can take hundreds or thousands of years to complete, subjecting the asteroids to temperature swings that range from the cold of deep space to the intense heating of close solar approaches. Despite these dramatic environmental changes, the transitions occur so gradually that thermal equilibrium is maintained throughout each orbital phase. The slow thermal cycling experienced by eccentric orbit asteroids creates unique conditions for geological processes that operate nowhere else in the solar system. During their cold phases, any volatile materials on their surfaces remain frozen and stable, while their warm phases allow for sublimation and chemical reactions that would be impossible in the consistently cold environment of the main asteroid belt. This thermal variability may have played important roles in the chemical evolution of these bodies over geological time. The phenomenon of asteroid pairs, where two objects share remarkably similar orbits and compositions, provides evidence for splitting events that occurred within the last few million years of solar system history. These paired asteroids represent the most recent examples of large-scale disruption processes where single bodies separated into multiple components while maintaining nearly identical trajectories through space. The similarities in their orbital elements are so precise that they could only result from a common origin in the very recent past, by astronomical standards. The formation of asteroid pairs demonstrates that large-scale geological processes continue to operate in the modern solar system, reshaping existing bodies through mechanisms that were more common during the chaotic early phases of planetary formation. The splitting events that create these pairs may result from rotational instabilities, where increasing spin rates eventually overcome the weak gravitational forces holding rubble pile asteroids together, causing them to gently separate into multiple components that continue traveling along similar paths. Binary asteroid systems sometimes exhibit complex orbital dynamics, where the two components undergo periodic changes in their separation distance, creating elliptical mutual orbits that vary from close approaches to wider separations over timescales of months or years. These orbital variations can be triggered by external perturbations such as planetary gravitational influences or impacts that alter the energy balance of the binary system. The resulting orbital evolution can persist for millions of years as the system gradually settles into a new equilibrium configuration. The study of binary orbital evolution provides insights into how gravitational systems respond to external disturbances, demonstrating principles that apply to everything from planetary ring systems to galaxy interactions. These miniature gravitational laboratories allow scientists to observe and model processes that operate on much larger scales throughout the universe, showing how matter organizes itself under the influence of gravitational forces across all size scales from asteroid pairs to galaxy clusters. Some asteroids contain impact breccias, rock formations created when fragments from multiple collision events became cemented together over time to form heterogeneous materials that preserve records of numerous impact episodes. These breccias contain clasts and fragments from different sources, creating geological puzzles where materials from various time periods and impact events are mixed together in complex patterns. The formation of these composite rocks occurred slowly as repeated impacts delivered new materials that were incorporated into existing regolith deposits through gradual compaction and cementation processes. The study of impact breccias reveals the complex history of bombardment that each asteroid has experienced, showing how multiple generations of impacts have contributed to the current surface compositions and structures. Some breccias contain fragments that originated from impacts occurring billions of years apart, creating temporal mixtures that span vast portions of solar system history. These materials serve as natural archives that preserve samples from many different impact events in single rock specimens. The thermal conductivity of asteroid materials affects how heat flows through these bodies, creating temperature gradients that extend from sun-heated surfaces into the cold interiors, where conditions remain nearly constant year-round. The poor thermal conductivity of most rocky materials means that solar heating penetrates only a few meters below the surface, leaving deeper regions insulated from the temperature variations that affect surface layers. This thermal stratification creates distinct zones within asteroids where different physical and chemical processes operate under different temperature regimes. The thermal isolation of asteroid interiors preserves materials in conditions that have remained essentially unchanged since these bodies formed billions of years ago, creating natural laboratories where pristine samples of early solar system materials might still exist in their original states. These protected environments may contain organic compounds, water ice, and mineral assemblages that have been completely altered or destroyed in more thermally active regions closer to asteroid surfaces. Asteroid surface features called lineae appear as long, straight, or gently curved markings that extend for kilometers across crater floors and intercrater plains, possibly formed by tectonic processes operating under the unique conditions of low gravity and weak internal structure. These linear features suggest that even small, rubble pile asteroids can experience forms of crustal deformation, where internal stresses create fracture patterns that manifest as surface expressions of deeper structural adjustments. The formation of lineae may occur over thousands of years as asteroids gradually respond to rotational changes or tidal stresses. The presence of tectonic features on asteroids challenges traditional views of these bodies as geologically inactive, showing that even the smallest worlds can undergo structural evolution over geological timescales. The lineae represent evidence that asteroid interiors are not completely rigid, but can respond to stress through slow deformation processes that eventually become visible as surface features. These discoveries expand our understanding of how geological processes operate under conditions very different from those found on terrestrial planets. Some asteroids show evidence of having experienced hydrothermal alteration early in their histories, when liquid water circulated through their interiors and chemically modified their mineral compositions. This alteration occurred during the first few million years after asteroid formation, when radioactive decay provided enough heat to melt ice and drive fluid circulation systems similar to those found in terrestrial geothermal environments. The hydrothermal processes created new mineral assemblages and redistributed chemical elements in ways that can still be detected in meteorite samples billions of years later. The evidence for ancient hydrothermal systems in asteroids suggests that these small worlds once hosted environments that might have been suitable for prebiotic chemistry or even primitive life forms. The circulation of warm, chemically active fluids through porous rock matrices could have facilitated complex chemical reactions that produced organic compounds and other materials relevant to astrobiology. These ancient aqueous environments represent some of the earliest habitable conditions that may have existed in the solar system. The rotational evolution of asteroids involves complex interactions between various forces, including solar radiation pressure, tidal effects from planetary encounters, and the Yarkovsky effect, where thermal emission creates tiny but persistent thrust forces that can significantly alter trajectories and rotation rates over millions of years. These subtle influences operate continuously but so slowly that their effects become apparent only over geological timescales, gradually modifying asteroid spins and orbits in ways that can eventually lead to dramatic changes in their dynamical behavior. The Yarkovsky effect demonstrates how even the simple act of absorbing and re-emitting sunlight can create forces capable of moving asteroids across the solar system over long periods. This thermal rocket effect occurs because asteroids absorb solar energy during their day sides and radiate it away from their night sides, creating a net thrust that can either accelerate or decelerate their orbital motion depending on their rotation direction. The cumulative effect of this tiny force can transport asteroids from the main belt into Earth-crossing orbits over millions of years. Deep impact craters on asteroids sometimes preserve central uplift features that formed when the shock waves from large impacts caused temporary rebound of the crater floor, creating peaks that rose from the impact site before solidifying into permanent topographic features. These central peaks provide windows into the subsurface structure of asteroids, exposing materials that were originally buried beneath the surface and revealing information about internal composition and structure that would otherwise remain hidden. The formation of central peaks in asteroid impact craters demonstrates how solid materials can behave like fluids under extreme shock conditions, temporarily losing their rigidity and flowing in response to pressure waves before solidifying again as the shock effects dissipate. This process creates permanent geological records of the intense forces generated during large impact events, preserving evidence of conditions that existed for only seconds during catastrophic collisions billions of years ago. Some asteroids contain veins of secondary minerals that formed when fluids carrying dissolved materials flowed through fractures in the asteroid's interior, depositing new mineral phases along crack walls and filling void spaces with crystalline materials. These mineral veins provide evidence of fluid circulation systems that operated within asteroids during their early histories, when internal heat sources drove hydrothermal processes that chemically altered the original rock compositions. The veins preserve records of the chemical conditions that existed within asteroid interiors billions of years ago. The study of secondary mineral assemblages in asteroids reveals information about the temperature, pressure, and chemical conditions that existed during fluid circulation events, providing insights into the internal environments that characterize these bodies during their most geologically active periods. Some veins contain minerals that could only have formed under specific conditions of temperature and fluid chemistry, creating natural thermometers and chemical sensors that record ancient environmental conditions preserved in crystalline form. The asteroid Psyche appears to be composed almost entirely of metallic iron and nickel, possibly representing the exposed core of a much larger differentiated body that was stripped of its rocky exterior by catastrophic impacts billions of years ago. This unique world provides an unprecedented opportunity to study planetary core materials directly, offering insights into the high-pressure, high-temperature processes that operated deep within planetesimals during the early phases of solar system evolution. The metallic composition of Psyche makes it one of the most unusual objects in the asteroid belt. The surface of Psyche likely gleams with the dull luster of weathered metal, creating a landscape unlike anything found elsewhere in the solar system. Solar wind bombardment and micrometeorite impacts have probably created a thin regolith of metal particles and impact glass, while the lack of rocky materials means that traditional geological processes operate in completely different ways than on silicate-rich worlds. The study of this metallic asteroid could revolutionize our understanding of planetary differentiation and core formation processes. Asteroid families created by catastrophic disruption events sometimes show evidence of subsequent collisional evolution, where family members have continued to interact with each other and with background populations of smaller projectiles over millions of years following the initial breakup. This ongoing evolution means that asteroid families are not static remnants of single disruption events, but continue to change as their constituent members experience additional impacts, rotational evolution, and orbital modifications that gradually alter their physical and dynamical properties. The long-term evolution of asteroid families provides natural laboratories for studying how collision processes operate over different timescales, from the instantaneous disruption that creates initial fragments to the gradual modifications that accumulate over millions of years of subsequent bombardment and dynamical evolution. Some family members show evidence of having been fractured and gravitationally reaccumulated multiple times, creating complex internal structures that preserve records of multiple generations of collision and reformation processes. Tonight, as consciousness gently dissolves toward the peaceful embrace of sleep, these countless ancient travelers continue their eternal voyage through the star-swept darkness, each one a silent witness to the patient processes that have shaped our cosmic neighborhood over billions of years of quiet evolution. They drift through space with the unhurried dignity of deep time itself, following gravitational pathways that were carved when the solar system was young and will endure long after the final planetary orbits have decayed into the cosmic night. In their gentle tumbling motions and predictable trajectories, they embody a kind of celestial meditation that speaks to the fundamental harmony underlying all existence, moving through the infinite void like ancient stones carrying whispered memories from the very dawn of time, forever traveling the invisible highways that connect the worlds of our solar system in an endless dance of gravity and motion that transcends all human understanding of permanence and change. The study of asteroid mineralogy reveals crystalline structures that formed under conditions of extreme slow cooling, where molten materials had millions of years to organize themselves into perfect geometric arrangements that would be impossible to achieve in terrestrial environments. These slowly cooled minerals display exceptional clarity and structural perfection, with crystal lattices that grew undisturbed by atmospheric interference or rapid temperature changes. The resulting formations represent some of the most pristine examples of natural crystallization processes in the solar system. What makes these slowly formed crystals particularly remarkable is their stability and durability. Having cooled over geological timescales, they achieved energy states so low that they can persist unchanged for billions of years without degradation. These perfect crystalline arrangements preserve atomic-level information about the conditions that existed during their formation, creating molecular libraries that contain detailed records of ancient environmental conditions encoded in their internal structures. Some asteroids exhibit evidence of magnetic field interactions that occurred during their formation when the early solar system contained magnetic fields much stronger than those present today. These interactions left permanent signatures in iron-bearing minerals that became magnetized during cooling, preserving fossil records of electromagnetic conditions that existed billions of years ago. The magnetic signatures are so stable that they continue to influence the behavior of charged particles in the vicinity of these asteroids today. The preservation of ancient magnetic information in asteroid materials provides unique insights into the electromagnetic environment of the early solar system, revealing details about magnetic field strengths and orientations that shape the formation of planetary systems. These paleomagnetic records represent the oldest magnetic information accessible to scientific study, offering glimpses into electromagnetic processes that operated when the solar nebula was still present and planetary formation was actively occurring. Asteroid surfaces display evidence of electrostatic levitation, where fine dust particles become charged through interactions with solar wind and cosmic rays, causing them to lift off the surface and hover in the weak gravitational fields for extended periods. This phenomenon creates ephemeral dust clouds that rise and fall with the changing electromagnetic environment around each asteroid, forming temporary atmospheres of charged particles that respond to variations in solar activity and interplanetary magnetic field conditions. The electrostatic levitation of dust particles demonstrates how electromagnetic forces can dominate over gravity in the unique environment of small airless bodies, creating dynamic systems where surface materials can become temporarily airborne without any atmospheric processes. These levitated particles eventually settle back to the surface, but their temporary suspension creates constantly changing patterns of dust distribution that modify the optical properties and thermal characteristics of asteroid surfaces. Binary asteroid systems sometimes experience resonant libration, where the orbital motion of the two components becomes coupled to their rotational periods in ways that create stable, oscillating patterns lasting for millions of years. These resonant relationships involve complex interactions between gravitational forces, tidal effects, and rotational dynamics that produce periodic variations in orbital separation and orientation. The resulting motion patterns create intricate gravitational dances where both components follow precisely choreographed routines that repeat with mathematical regularity. The study of resonant libration in binary asteroids provides insights into how gravitational systems naturally organize themselves into stable configurations that minimize energy while maintaining dynamic equilibrium. These systems demonstrate principles of celestial mechanics that apply across all scales of cosmic structure, from planetary ring systems to galactic dynamics, showing how matter responds to gravitational influences by creating ordered patterns that persist over cosmic timescales. Some asteroids contain shock-induced diamonds formed during high-velocity impact events when carbon-bearing materials were subjected to pressures and temperatures sufficient to transform graphite into crystalline diamond structures. These impact diamonds are typically microscopic in size but extremely numerous, creating dispersed populations of gemstone materials throughout the asteroid structure. The diamonds preserve precise records of the shock conditions that created them, providing natural pressure gauges that reveal the intensity of ancient collision events. The formation of impact diamonds requires specific combinations of pressure, temperature, and duration that occur only during the most energetic collision processes, making these materials valuable indicators of the most extreme events in asteroid collision history. The survival of these diamonds over billions of years demonstrates the stability of crystalline carbon under space conditions, where the absence of weathering processes allows these precious materials to persist indefinitely in their original forms. Asteroid regoliths often contain spherical glass beads formed when impact melting created droplets of molten rock that cooled rapidly while suspended in the vacuum of space. These impact glasses preserve chemical compositions that represent mixtures of materials from both the impacting projectile and the target asteroid, creating composite compositions that record the details of specific collision events. The spherical shapes result from surface tension effects operating on liquid droplets in zero gravity, producing perfectly round particles that could never form under terrestrial conditions. The glass beads found in asteroid regoliths serve as natural time capsules that preserve samples of materials from throughout the solar system, carried to each asteroid by impacting projectiles that originated in different regions of interplanetary space. The chemical compositions of these glasses can sometimes be traced back to their source regions, revealing the complex history of material transport that has operated throughout solar system evolution. Deep crater analysis on asteroids reveals evidence of layered structures within these bodies, where different episodes of accretion created distinct compositional zones that become visible when exposed by large impact events. These stratigraphic sequences preserve records of the changing conditions that existed during asteroid formation, showing how material properties varied over time as different types of debris were incorporated into growing planetesimals. The layered structures provide cross-sectional views through asteroid interiors that would otherwise remain hidden from observation. The exposure of internal layering through impact excavation creates natural geological surveys, that reveal information about asteroid composition and structure without requiring direct sampling missions. Large craters essentially perform archaeological excavations that expose materials from different depths and formation periods, creating opportunities to study the internal architecture of asteroids through remote sensing techniques applied to crater walls and central peak formations. Some asteroids show evidence of having experienced multiple thermal metamorphism events throughout their histories, where repeated heating episodes gradually altered their mineral compositions and crystal structures over billions of years. These thermal modifications occurred during different phases of asteroid evolution, including initial accretional heating, radioactive decay warming, and possible later heating due to orbital changes or impact events. The cumulative effects of multiple thermal episodes created complex mineral assemblages that preserve records of changing temperature conditions over geological time. The study of thermal metamorphism in asteroids reveals how these bodies responded to various heat sources throughout solar system history, showing that even small worlds can experience complex thermal evolution involving multiple heating and cooling cycles. The mineral transformations that resulted from these thermal processes provide natural thermometers that record the temperature histories of asteroid interiors, offering insights into the energy sources and thermal processes that shaped these ancient worlds. Asteroid dust analysis reveals particles with isotopic compositions that differ from typical solar system materials, suggesting the presence of pre-solar grains that formed around other stars before being incorporated into our solar nebula. These interstellar particles preserve chemical signatures of stellar nucleosynthesis processes that occurred in distant stars billions of years ago, making them among the oldest materials accessible for laboratory study. Their survival within asteroid matrices demonstrates the gentle nature of early solar system accretion processes that preserved fragile interstellar materials. The discovery of pre-solar grains in asteroid materials provides direct samples of matter that formed in stellar environments very different from our Sun, offering unique insights into the chemical processes that operated in other stellar systems throughout galactic history. These ancient particles serve as astronomical specimens that can be studied in terrestrial laboratories, bridging the gap between cosmochemistry and stellar astrophysics through analysis of materials that witness the birth and death of stars. Surface age dating of asteroid terrains using crater counting techniques reveals that some regions have been exposed to space for billions of years, while others show evidence of much more recent exposure, possibly due to impact events that excavated subsurface materials or mass wasting processes that redistributed surface layers. These age variations create complex temporal mosaics where materials from different epochs are exposed side by side, providing opportunities to study how asteroid surfaces have evolved over different timescales. The coexistence of ancient and young surface materials on individual asteroids demonstrates that these bodies continue to experience geological processes that modify their appearances over time, challenging views of asteroids as completely inactive worlds. The processes responsible for surface renewal operate slowly but persistently, gradually exposing fresh materials and burying older surfaces through mechanisms that may include impact gardening, thermal cycling, and rotational effects. Some asteroids contain mineral assemblages that could only have formed in the presence of liquid water at elevated temperatures, indicating that hydrothermal systems operated within these bodies during their early histories when radioactive heating provided sufficient energy to maintain liquid water circulation. These aqueous alteration products preserve detailed records of the chemical conditions that existed within asteroid interiors, including information about fluid compositions, temperatures, and circulation patterns that shaped early asteroid geology. The evidence for ancient hydrothermal activity in asteroids suggests that these small worlds once hosted chemical environments similar to those found in terrestrial hot springs, where complex chemical reactions could have produced organic compounds and other materials relevant to astrobiology. These ancient aqueous systems represent some of the earliest potentially habitable environments in the solar system, existing before Earth had developed stable surface conditions suitable for life. Binary asteroid formation mechanisms involve complex processes where single objects can split into multiple components through rotational instability, tidal disruption during planetary encounters, or gentle collisions that separate weakly bound rubble pile structures. The resulting binary systems often maintain remarkably stable orbital configurations that can persist for millions of years, demonstrating how gravitational forces naturally organize debris into ordered arrangements that maximize stability while preserving the individual identities of component bodies. The formation and evolution of binary asteroids provide natural experiments in gravitational dynamics that reveal how matter organizes itself under the influence of competing forces, including gravity, rotation, and tidal effects. These systems serve as laboratories for studying fundamental principles of celestial mechanics that apply to gravitational interactions throughout the universe, from planetary ring particles to binary star systems. Asteroid surface composition mapping reveals regional variations that reflect different formation conditions or subsequent modification processes, creating chemical landscapes where various minerals are distributed in patterns that tell stories about each body's geological history. Some asteroids display compositional gradients that may reflect thermal processing during formation, while others show evidence of impact mixing that has redistributed materials across their surfaces over billions of years of bombardment history. The chemical heterogeneity observed on asteroid surfaces provides insights into the diversity of conditions that existed during early solar system evolution, showing how local variations in temperature, pressure, and chemical environment created the complex array of materials that characterize these ancient worlds. Each compositional domain preserves information about specific formation conditions, creating natural archives of early solar system chemistry. Some asteroids exhibit unusual optical properties that change dramatically depending on viewing geometry, suggesting surface structures that scatter light in complex ways due to unusual particle sizes, shapes, or arrangements. These optical effects may result from impact processes that created specific types of regolith textures, or from the presence of unusual minerals that interact with sunlight in distinctive ways. The varying reflectance properties create surfaces that appear to change brightness and color as they rotate, producing optical phenomena visible from Earth-based telescopes. The study of unusual asteroid optical properties provides insights into surface physical processes that operate under the unique conditions of airless, low-gravity environments where normal terrestrial weathering mechanisms are absent. These optical variations preserve information about surface modification processes that may be unique to small solar system bodies, offering opportunities to study geological processes that have no terrestrial analogs. Deep interior modeling of large asteroids suggests that some may contain partially differentiated structures where dense materials have settled toward their centers without achieving complete separation into distinct core and mantle regions. These partially differentiated bodies preserve records of the thermal processes that operated during early asteroid evolution, showing how internal heating affected different types of materials and created complex internal architectures that reflect the competition between gravitational settling and thermal convection processes. The study of partial differentiation in asteroids reveals how thermal evolution proceeds in small bodies, where heating rates, cooling times, and internal structure all differ significantly from conditions that existed in larger planetesimals that became fully differentiated planets. These intermediate cases provide insights into the threshold conditions that determine whether rocky bodies develop layered internal structures or retain more homogeneous compositions throughout their evolution. Asteroid orbital resonances create invisible architectural frameworks throughout the solar system where gravitational forces organize matter into stable patterns that persist over cosmic timescales. These resonant structures demonstrate how gravity naturally creates order from apparent chaos, establishing regions where asteroids can exist safely for billions of years while clearing other zones of debris through dynamical instability. The resulting orbital architecture reflects the deep mathematical relationships that govern planetary motion and influence the distribution of matter throughout planetary systems. The resonant patterns that shape asteroid orbits reveal the hidden influence of planetary gravity acting across vast distances to organize smaller bodies into predictable arrangements that follow precise mathematical rules. These gravitational architectures create cosmic order that extends far beyond planetary orbits themselves, establishing frameworks that influence the motion of countless smaller objects throughout the entire solar system volume. Surface thermal modeling of asteroids reveals complex temperature distributions that vary with latitude, local topography, and thermal properties of surface materials, creating intricate thermal landscapes where different regions experience vastly different heating and cooling cycles despite being part of the same rotating body. These thermal variations drive physical and chemical processes that operate at different rates in different locations, creating spatially variable environments that may preserve materials with very different thermal histories on the same asteroid. The thermal heterogeneity of asteroid surfaces creates natural laboratories where materials experience different environmental conditions while remaining accessible for comparative study, offering opportunities to investigate how thermal processing affects various types of materials under controlled conditions. These thermal variations preserve records of how surface properties influence the response of different materials to space weathering and thermal cycling over geological timescales. Some asteroids contain evidence of impact vapor deposits, where the most energetic collision events created sufficient heat to vaporize portions of both projectiles and targets, creating gaseous clouds that subsequently condensed onto surrounding surfaces as thin coatings of exotic materials. These vapor deposits preserve chemical signatures of the most extreme impact processes, where kinetic energy was converted to heat sufficient to change solid materials into gas phases before recondensation created new mineral assemblages with unusual compositions and structures. The study of impact vapor deposits provides insights into the highest energy collision processes that have operated throughout solar system history, revealing how the most catastrophic events created unique materials through processes that cannot be replicated in laboratory experiments. These deposits serve as natural records of extreme impact conditions that produce temperatures and pressures exceeding those found in most terrestrial environments. Binary asteroid tidal evolution involves gradual changes in orbital separation, driven by energy dissipation through internal friction, as gravitational forces raise tides within both components of the system. This process operates over millions of years, slowly causing binary asteroids to either spiral closer together toward eventual merger, or drift farther apart toward eventual separation, depending on the initial conditions and physical properties of the component bodies. The tidal evolution creates predictable changes in orbital characteristics that can be modeled mathematically and observed through long-term monitoring campaigns. The study of tidal evolution in binary asteroids provides natural examples of how gravitational systems respond to energy dissipation processes, demonstrating fundamental principles of celestial mechanics that apply to tidal interactions throughout the universe. These systems serve as accessible laboratories for studying tidal physics that operates on timescales and under conditions that make direct experimental study impossible for larger gravitational systems like planet-moon pairs. Asteroid mineral weathering proceeds through mechanisms that have no terrestrial counterparts, involving interactions between solar wind particles, cosmic rays, and surface materials that gradually alter crystal structures and chemical compositions over millions of years of space exposure. These space weathering processes create surface modifications that accumulate slowly but persistently, eventually transforming the optical and physical properties of asteroid surfaces in ways that can be detected through spectroscopic observations from Earth. The unique weathering environment of airless asteroid surfaces allows for chemical and physical processes that cannot occur in terrestrial environments, creating opportunities to study material modification mechanisms that operate under extreme conditions of vacuum, radiation, and temperature cycling. These processes produce surface alteration products that preserve records of the space environment conditions that have existed throughout solar system history. Tonight, as you drift toward the gentle realm of dreams, these countless ancient voyagers continue their patient journey through the cosmic depths, each one a silent guardian of memories that stretch back to the very beginning of our solar system story. They move through space with the timeless grace of eternity itself, following paths carved by gravity's invisible hand when the stars were young and the planets were still finding their places in the cosmic dance. In their quiet rotation and steady orbital progress, they carry forward the whispered secrets of 4 billion years, traveling the dark highways between worlds with a serenity that transcends all earthly measures of time and change. Their surfaces, polished by eons of cosmic weathering, reflect starlight that has journeyed across unimaginable distances to illuminate these wandering worlds, creating a gentle luminescence that speaks to the fundamental interconnectedness of all matter and energy throughout the vast cathedral of space. As sleep approaches with its own quiet inevitability, these stellar companions continue their eternal pilgrimage through the darkness, bearing witness to the patient processes that have shaped not only our solar system but countless others throughout the galaxy. Their silent presence a reminder that we are all participants in a cosmic story that began with the first stirrings of matter and energy in the primordial universe, and will continue long after the final stars have exhausted their nuclear fires and faded into the infinite night. The process of crater chain formation on asteroids reveals evidence of secondary impact cascades, where debris ejected from primary impacts travels in ballistic trajectories across the asteroid's surface, before creating secondary craters arranged in linear patterns that can extend for kilometers. These crater chains preserve detailed records of impact dynamics, showing how ejecta clouds expand and settle under the influence of weak gravitational fields that allow particles to travel much farther than would be possible on more massive worlds. The secondary impacts often occur hours or days after the initial collision, creating time-delayed geological events that unfold in slow motion across asteroid landscapes. The formation of these secondary crater chains demonstrates how single impact events can trigger complex sequences of surface modification that continue long after the primary collision has ended. The ballistic trajectories followed by ejecta particles depend on the asteroid's rotation rate, gravitational field strength, and surface topography, creating unique patterns that reflect the specific physical characteristics of each world. These chains serve as natural experiments in low-gravity ballistics that reveal how projectile motion operates under conditions very different from terrestrial environments. Some asteroids display evidence of thermal segregation, where repeated heating and cooling cycles have caused different types of materials to separate based on their thermal expansion properties, creating compositional layering that developed over millions of years of temperature cycling. This process operates through differential thermal expansion, where materials with different coefficients of expansion gradually migrate to different depths within the regolith, as thermal cycling creates microscopic movements that accumulate over geological time into macroscopic sorting patterns. The thermal segregation of asteroid regoliths creates naturally sorted deposits where materials with similar thermal properties become concentrated in specific layers or regions, forming compositional gradients that reflect the thermal history experienced by each location. These segregated deposits preserve information about the long-term thermal environment that has characterized different parts of asteroid surfaces. creating archives of thermal conditions that span millions of years of orbital evolution. Asteroid collision modeling reveals that many impact events result in net accretion rather than erosion, where incoming projectiles stick to target surfaces despite impact velocities that would cause fragmentation in terrestrial environments. The weak gravitational fields and porous structures of many asteroids allow them to absorb impact energy more effectively than solid bodies, enabling them to capture and retain debris that would otherwise escape into space. This accretional process has gradually increased the masses of some asteroids over billions of years of bombardment. The accretional nature of many asteroid impacts demonstrates how these bodies can grow through collision processes rather than being eroded away, challenging traditional views of impact bombardment as purely destructive. The ability of asteroids to capture and retain impact debris depends on complex interactions between projectile velocity, target structure, and gravitational binding energy, creating conditions where collisions can either build up or tear down these ancient worlds depending on the specific circumstances of each encounter. Binary asteroid orbital decay sometimes results in extremely gentle merger events where two components come together at velocities so low that both bodies remain largely intact while forming contact binary configurations that preserve evidence of their dual origin in their elongated shapes. These slow-motion collisions occur over thousands of years as tidal forces gradually reduce orbital separation until the surfaces of both components eventually touch, creating unified objects that maintain distinct lobes representing their previous independent existence. The formation of contact binaries through orbital decay demonstrates how gravitational systems can evolve toward minimum energy configurations through processes that unfold over timescales vastly longer than typical collision events. These gentle mergers preserve internal structures and surface features that would be destroyed in higher velocity impacts, creating composite objects that serve as natural archives of binary evolution processes operating under the unique conditions of low-mass gravitational systems. Some asteroids exhibit seasonal albedo variations that result from the migration of fine particles across their surfaces in response to thermal cycling, where daily temperature changes cause expansion and contraction of surface materials that gradually redistribute dust and debris in patterns that change with orbital position. These albedo cycles create surfaces that appear to breathe with their orbital rhythm, becoming brighter or darker as different materials are exposed or buried through the slow dance of thermal expansion and contraction. The seasonal redistribution of surface materials demonstrates how even the most subtle environmental changes can produce measurable effects on asteroid surfaces over time, showing that these apparently static worlds actually experience dynamic processes that operate on timescales accessible to human observation. These variations preserve records of how surface properties respond to thermal cycling, creating natural experiments in regolith dynamics that reveal the complex interactions between temperature, particle size, and surface mobility. Asteroid magnetic anomalies detected by spacecraft reveal localized magnetic field concentrations that may represent remnants of ancient core dynamos or impact-generated magnetic signatures preserved in metallic components of these bodies. These magnetic features create invisible landscapes of field strength variations that influence the behavior of charged particles in the vicinity of asteroids, creating complex electromagnetic environments that vary dramatically across different regions of the same body. The preservation of magnetic signatures in asteroid materials provides evidence that some of these bodies once possessed internal magnetic fields generated by fluid motion in molten metallic cores, similar to the dynamo processes that operate in terrestrial planets. The survival of these magnetic signatures over billions of years demonstrates the remarkable stability of certain magnetic materials under space conditions, where the absence of atmospheric weathering allows ancient magnetic records to persist indefinitely. Deep regolith analysis on asteroids reveals stratified deposits where different layers preserve materials from distinct time periods, creating geological sequences that can be read like history books written in dust and debris. These stratigraphic records contain materials delivered by impacts occurring over millions of years, with each layer representing a specific epoch in the bombardment history experienced by that particular region. The preservation of these layered sequences requires stable conditions, where burial occurs faster than mixing processes can homogenize the deposits. The stratigraphic preservation of impact history in asteroid regoliths creates natural archives that contain samples from throughout the solar system, delivered by projectiles that originated in different regions and time periods. These layered deposits can potentially be sampled by future missions to provide chronological sequences of materials that document how the composition of impacting populations has changed over billions of years of solar system evolution. Asteroid shape evolution involves gradual modifications driven by impact gardening, thermal cycling, and rotational effects that slowly alter the overall morphology of these bodies over geological timescales. Large asteroids tend to become more spherical over time as impact processes smooth out irregular features and redistribute mass toward gravitationally stable configurations. Smaller asteroids may retain highly irregular shapes indefinitely due to their weak gravitational fields that cannot overcome structural irregularities inherited from their formation processes. The long-term evolution of asteroid shapes provides insights into how gravitational forces compete with other processes to determine the final morphology of small solar system bodies, showing that even weak gravitational fields can eventually overcome structural irregularities given sufficient time. These shape evolution processes operate so slowly that they require millions of years to produce noticeable changes, yet they demonstrate the persistent influence of fundamental physical forces acting over cosmic timescales. Some asteroids contain evidence of ancient volcanic activity in the form of basaltic materials that cooled from molten states billions of years ago, when radioactive heating provided sufficient energy to melt portions of their interiors and drive magmatic processes similar to those that shape terrestrial planets. These volcanic materials preserve records of high-temperature processes that operated within asteroid interiors during the earliest phases of solar system evolution, when heat sources were more abundant and thermal gradients were steeper than conditions that exist today. The volcanic history preserved in asteroid materials reveals that some of these bodies experience complete thermal evolution sequences involving heating, melting, differentiation, and cooling phases that transform their internal structures from homogeneous assemblages of primitive materials into layered arrangements with distinct chemical and physical properties. These evolutionary sequences demonstrate that asteroids could undergo geological processes similar to those that shaped much larger planetary bodies, albeit on reduced spatial and temporal scales. Asteroid dust grain analysis reveals particles with surface textures created by billions of years of micrometeorite bombardment, where each tiny impact has contributed to the gradual erosion and modification of individual grains through processes that operate on microscopic scales but accumulate into macroscopic changes over geological time. These surface textures preserve records of the intensity and duration of micrometeorite bombardment experienced by different regions of asteroid surfaces, creating grain-scale archives of impact history. The microscopic impact features preserved on asteroid dust grains provide information about the flux and characteristics of small projectiles that have bombarded these surfaces throughout solar system history, revealing details about debris populations that are too small to be observed directly, but whose effects accumulate over time into measurable modifications of surface materials. These microscopic records complement larger-scale crater statistics to provide comprehensive pictures of impact processes operating across all size scales. Binary asteroid mass transfer processes occasionally occur when material ejected from one component by impacts or rotational effects is captured by the gravitational field of its companion, creating slow exchanges of mass between the two bodies that can continue over millions of years. These mass transfer events gradually alter the size and composition distributions within binary systems, sometimes leading to significant changes in the relative masses of component bodies over geological timescales. The study of mass transfer in binary asteroids provides insights into how gravitational systems can evolve through material exchange processes, demonstrating mechanisms that may operate in other binary systems throughout the universe, including binary stars and planet-moon pairs. These processes reveal how gravitational capture can redistribute matter between closely paired objects, creating evolutionary pathways that would be impossible for isolated bodies. Asteroid thermal emission patterns reveal surface temperature variations that create complex thermal landscapes where different regions experience vastly different heating and cooling cycles despite their proximity to each other on the same rotating body. These temperature variations are controlled by factors including local topography, surface composition, thermal inertia, and exposure geometry, creating thermal environments that can vary by hundreds of degrees across distances of only a few kilometers. The thermal heterogeneity of asteroid surfaces creates natural laboratories for studying how different materials respond to identical external heating conditions, providing opportunities to investigate the thermal properties of various rock and mineral types under controlled environmental conditions. These thermal variations preserve information about surface composition and structure that can be detected through infrared observations, allowing remote sensing techniques to map material properties across entire asteroid surfaces. Some asteroids show evidence of impact melt migration, where molten materials created during large impacts flowed across surfaces under the influence of weak gravitational fields, before cooling and solidifying in locations far from their points of origin. These flow features preserve records of impact events energetic enough to create substantial volumes of molten rock, demonstrating that even relatively small asteroids can experience collision events capable of generating extreme temperatures and pressures. The migration of impact melts across asteroid surfaces creates geological features that have no terrestrial analogs, where molten rock flows behaved very differently under low gravity conditions than they would in Earth's stronger gravitational field. These flow features preserve information about impact dynamics and cooling processes that operated under the unique environmental conditions that characterize airless, low-gravity worlds. And so our gentle journey through the asteroid fields comes to its quiet end. We've drifted alongside these ancient wanderers, these patient guardians of cosmic memory, who have been traveling the dark spaces between worlds since before Earth knew the warmth of its first sunrise. In their silent orbits and endless tumbling, we've found a kind of peace that only comes from contemplating things that move at the pace of eternity itself, unhurried and serene in the vast cathedral of space, carrying within their rocky hearts the whispered stories of 4 billion years. Sweet dreams, and may you rest as peacefully as these timeless stones drifting through the infinite night.